You can ask Maxime. But basically, yeah, actually it was first introduced without exactly this terminology, but by Maxime Olchani and Vanya Dunko in 1D. And in 1D it's simpler because you can use a direct delta interaction directly. So you don't need to use a lattice model or these kind of things. Okay. By the way, I forgot to mention at the end of last lecture about the two-channel model. Remember, I told you that the number of closed channel molecules is equal to the contact times something. And this something actually becomes small if you are in the zero range regime. So in experiments, the number of closed channel molecules, if you are in the zero range regime, will be much smaller than the number of atoms, which of course is what you want. So you want to forget about the fact that you actually have a Feshbach resonance and all this, and you want, I mean, most of the time, you want to have an experiment which is in the universal regime, which is described by a zero range model. So today I will talk about symmetry properties at the unitary limit, and of course give some consequences. And for more details, you can look once again at the lecture notes in physics chapter that we wrote with Yvan, or at a paper that we wrote in 2006. Again, I put the references in the notes. And actually, today I will also follow some approach which is written in my PhD thesis. So I will consider today the zero range model, and I will consider the unitary limit, infinite scattering length, except for one part where I will say that it holds also for finite scattering length. So the first thing to note about the unitary limit, and Frédéric also already told you about it, is that you have a scale invariance. Because you have no length scale, which comes from the interactions. And for example, this implies the following. So let's consider a fixed number of spin up and spin down particles. And let's put them in a box of length L and at a temperature T. And now let's consider another system where the size of the box is multiplied by some factor lambda. And then it's easy to show that actually if we divide the temperature by lambda squared, keeping fixed the number of particles, then these two systems are absolutely equivalent. So of course you need to take into account the fact that you have to rescale the distances, but apart from that, these two systems are absolutely the same. And this implies that, for example, the equation of state, as Frédéric told you, can be written in terms of dimensionless variables. And it also implies, if you look at zero temperature, that the ground state energy is given by, the ground state energy per unit volume is given by the energy of the ideal gas multiplied by some dimensionless universal number psi, which is called the Birch parameter. But actually, there is more than that. And this is the topic of this chapter. So there is some hidden symmetry in addition to this, I would say, a trivial scale invariance. So in the first part, I will follow a somewhat pedestrian way to derive and to understand this symmetry. Namely, I will show you that there is a separability in so-called hyperspherical coordinates, so which of course I will define. So again, let's consider n up fermions of spin up and n down fermions of spin down. And let's consider that we have an external potential. So that was already the case at some point in the previous lecture. So let me consider that these fermions are subject to an external potential U of R. And now I will consider it to be harmonic and isotropic. So just 1/2 m omega squared r squared. And sometimes I will consider actually the case where omega is equal to 0, which means that in this case we are just in free space. So we will be looking at scattering between these n particles. So the wave function, let me denote it by capital phi. And of course, it's a function of R1 up to Rn. And sorry, let me put here R2. And actually, here it will be convenient to consider that the first particle has a spin up and the second particle has a spin down. And then the other particles can have whatever spin. Of course, this is just a matter of convention. So let me recall you the definition of the zero range model. So first of all, we have the Schrödinger equation minus h bar squared over 2m sum from I equal 1 to n Laplacian with respect to Ri phi. So that's the kinetic energy part. Then we have the trapping potential, so 1/2 m omega squared sum from I equal 1 to n Ri squared phi equal to the energy, and here I will call it E tot for total phi. And this should hold whenever all interparticle distances are non-zero. And then when some interparticle distance goes to 0, we have the contact condition. And I will write it directly in the case where the scattering length is infinite. And actually, I will write the contact condition only for the pair 1, 2 approaching each other. And that's actually enough because the wave function here should be antisymmetric. So if this contact condition is satisfied, then the other ones will automatically be satisfied as well. So the wave function should diverge like 1 over the distance r12 between the two particles times some constant a, which depends on the center of mass position of the two particles and on the positions of the other particles, plus higher order term. So actually in the following it will be convenient to rewrite the contact condition in the following way. If you take the derivative of r12 phi with respect to r12, and then you take the limit r12 going to 0, then this should be 0. So it's quite easy to check that this here is equivalent to this. And if you want to be accurate, this derivative here should be taken at a fixed direction of R12 and a fixed, again, a fixed center of mass of R12 and fixed positions of the other particles. So the reason for that is simple. So if you take this form, you multiply it by R12, so then you get here a constant, which once you take the derivative gives 0. And this higher order term, if you multiply it by R12, you get R12 squared. You take a derivative, you are back to R12, and this also gives 0 in the limit. So now let me separate the center of mass, C. So now the center of mass of all the particles. So 1 over n, sum from I equal 1 to n of Ri. And now a bit less common, let me introduce so-called Jacobi coordinates. Where the idea is the following. So let's say we have our particle positions like this. Then the first Jacobi coordinate will be just this vector going from the particle 1 to particle 2. And this one I will call it eta 2 because it goes to the particle 2. Then we will go to the particle 3, but we will start from the center of mass of 1 and 2. And this will be the Jacobi coordinate eta 3. And then we will start from the center of mass of the 3 particles and go to the particle 4, and so on. So it's easy to write down the general equation defining these etas. I will have it in the notes. And now let me define a vector capital R, which will be the collection of all of these Jacobi coordinates, and leave some space here. So it's the collection of all the eta j's from j equal 2 up to n. And it will be convenient to just rescale here by square root of j minus 1 over j. So this is a big vector, and the number of coordinates here is 3n minus 3. Okay, in the beginning we had n particles, so we had 3n coordinates, but here we removed the center of mass. Now we are looking only at the relative positions, so we have 3n minus 3 coordinates. And then, of course, we can write our wave function, phi of R1, Rn. We can rewrite it as a function of these new coordinates, center of mass and capital R. So for the relative coordinates. So actually there is a separability of the center of mass, meaning that this, for an eigenstate of our zero range model, this can be written as a product of some function psi cm of the center of mass times some function psi of r. And accordingly, the total energy, E tot, appearing here, can be written as a sum of center of mass energy plus energy E, which corresponds to the relative motions, internal energy, if you want. So, I mean, that's quite a well-known fact, and sometimes it's called Cohn's theorem. And for example, you can derive it, that's how I wrote it in the notes, you can derive it starting from a finite range model, where it's actually well known, and it's easy to show that you have this separability of the center of mass in a harmonic potential. So it's important here to have the harmonic potential. And then you can take the zero range limit and you conclude that the separability holds also for the zero range model. So, having done that, we now have a problem for the zero range model problem, which concerns only the internal motion. So, more precisely now, the Schrödinger equation for this internal wave function psi looks as follows. So minus h bar squared over 2m Laplacian with respect to r of psi. So remember, r is this big vector which contains all the coordinates, plus 1/2 m omega squared r squared psi equal to e psi. And the contact condition here, well, obviously it's now looks like as follows. It's the derivative of eta 2. I mean, it's r12, but now since we are using these Jacobi coordinates, I will write it eta 2 times the wave function psi with respect to eta 2 for eta 2 going to 0 is equal to 0. And now this derivative should be taken at a fixed direction of eta 2 and the fixed values of the other Jacobi coordinates eta 3, eta 4, and so on. Okay, so far we have not done anything very interesting, but now let me introduce these hyperspherical coordinates. Which are simply defined as follows. So first, there is the so-called hyperradius, capital R, which is just the norm of this big vector R. Okay, so it's the square root of the sum of all these Jacobi coordinates squared. And actually it turns out that this is also equal to the square root of 1 over n sum over I and j of rij squared. So you see that this hyperradius is just proportional to the root mean squared interparticle distance. So basically it tells you whether your particles are far apart on average, or if the hyperradius is small, it means that all the particles are close together. So that's the hyperradius. And then we also have hyperangles. So, and they just correspond to this r hat, which is the unit vector r divided by the norm of r. So this is a unit vector in this space of 3n minus 3 dimensions. And so, therefore, it can be parameterized by 3n minus 4 angles, which are called hyperangles. Okay, if you have a unit vector in 3D, it's parameterized by 2 angles. So now if you are in 3n minus 3 dimensions, you have 3n minus 4 angles. And let me actually define these angles so that everything is concrete. So so the collection of these angles, I will denote them by capital omega. And this capital omega is given by the following collection of angles. So first of all, you have the angles that correspond to the direction of each of these Jacobi vectors. So these are unit vectors in 3D. So this is two angles. So each of them corresponds to two angles. And then you have other angles that I will call alpha 2 up to alpha n minus 1. And they are defined as follows. So first of all, they are between 0 and pi over 2. And second, they satisfy the following equations. So eta 2 is equal to r, so the hyperradius, times sinus of alpha 2. Then eta 3 is equal to r times cosine alpha 2 times sine alpha 3, and so on. So until you arrive at eta n minus 1, which is r cosine alpha 2, cosine alpha 3, etc., cosine alpha n minus 1, and then sine, sorry, that's n minus 2, sine alpha n minus 1, and finally eta n, which is r cosine alpha 2, etc., all the same, except that at the end you put a cosine alpha n minus 1. So by the way, if you worry that indeed these angles exist and they are unique, actually you should first define alpha n minus 1 by taking a ratio of the last two equations, and then define alpha n minus 2 and so on. Okay, so having defined these hyperradius and hyperangles, again, of course, now our wave function for the internal coordinates, for the internal motion, psi of r, vector r, can be written as a function of hyperradius and hyperangles. And now, the very important fact is that there is separability between the hyperradius and the hyperangles. Meaning that this, for any eigenstate of the zero-range model, so satisfying these equations, this can be written as a product of some function g of the hyperradius times some function phi of the hyperangles. And that's a really non-trivial fact. And let me explain why it's true. So first of all, the contact condition, which is written here, it actually only constrains the omega dependence of the many-body wave function. So it doesn't constrain the hyperradius dependence, the r dependence. And you can see this just by writing down explicitly this contact condition in terms of the hyperangles. And you can show quite easily that the contact condition in terms of the hyperangles, it looks as follows. It's a derivative of sine alpha 2 times the wave function with respect to alpha 2 taken at alpha 2 going to 0 equal to 0. So basically it's just because you see this alpha 2, this eta 2 here is equal to sinus alpha 2, so that's where you get sinus alpha 2 here, times the hyperradius, but this hyperradius actually will cancel out with this differential of eta 2. And again, if you want to be precise, this derivative now is taken at fixed values of alpha 3 up to alpha n minus 1, so all the other hyperangles, and also all these ones. And also fixed value of the hyperradius. So that's how you see that this contact condition actually, it only puts a constraint on the hyperangular dependence of your wave function. And note that actually this cannot be true if you have a finite scattering length. For a very simple reason. So such a contact condition which acts only on the angles, of course it must be dimensionless because the angles are dimensionless. So therefore, if you have a finite scattering length, your boundary condition, your contact condition here, because it's dimensionless, it should depend on the ratio scattering length divided by hyperradius. That's the only other length that you have. And therefore, it will couple the hyperangles with the hyperradius. So basically, you will have something in the right-hand side here, which will be a function of hyperradius. So in that case, you don't have the separability. So, so that's the main reason why there is separability. And then there is another more trivial reason, which is that the Schrödinger equation here is also separable. Because it can be written as follows in hyperspherical coordinates: minus h bar squared over 2m times second derivative with respect to hyperradius plus 1 over r times the first derivative plus 1 over r squared times something that I call T omega, which is just a differential operator which acts on the hyperangles. So it's some combination of derivatives with respect to the angles. And sometimes this is called the Laplacian on the hypersphere. And then, of course, we have the trapping potential, 1/2 m omega squared r squared, psi equal e psi. So this is indeed also compatible with separability, because you see that this depends only on hyperradius, and this thing is a product of something that depends on the hyperradius and something that depends on the angles. So you can make this ansatz. You inject it into the Schrödinger equation, and you will get indeed two completely separated problems. So first of all, you have the hyperangular problem. Which looks as follows. So, sorry. T omega acting on phi of omega should be equal to some eigenvalue that I will call minus s squared for later convenience times phi of omega. So phi of omega has to be an eigenvector of this operator. And I mean, this is a little bit analogous to what you do if you do, for example, the hydrogen atom, and you introduce hyperspherical harmonics, and then your hyperspherical harmonics have to be eigenvalues of the angular momentum squared operator with eigenvalues L plus 1. So here it's a bit a similar story, except that instead of being in 3D, we are in a higher dimensional space. And these eigenvalues have no reason to be LL plus 1 or anything simple. So they are just some real positive numbers. And then, of course, you have the contact condition, which, because it acts only on the angles, it can be written now as a condition on this angular wave function phi. So I just need to copy what's written here, but now it's for the wave function phi. So derivative of sine alpha 2 phi with respect to alpha 2 at alpha 2 equals 0 equals 0. So you see that, I mean, we started from a many-body problem with strong interactions at the unitary limit, and there is no magic. We still have a very difficult problem here because we have many hyperangles, and we have these contact conditions which encode the interactions. So that's a very good question, and actually for now you should just believe me, that's how it is. And in fact I will come back to that. So in some situations for bosons, for example, actually this guy becomes positive, and then the situation changes dramatically. But for fermions, with if you have equal mass of spin up and spin down, this actually is always a real negative, as far as we know, and I will come back to it. So actually, thanks for asking. So everything that I wrote down here actually holds when the number of particles is bigger or equal to 3. You should not try to do this business for 2 particles. And the reason is very simple, because you see that if you have 2 particles, actually the contact condition now will act on the hyperradius, because for 2 particles the hyperradius is just the distance between the 2 particles. So then the story is different. So that's the hyperangular problem, and now there is also, of course, the hyperradial problem. And while this one is in general very difficult, this one is actually extremely simple. So first of all, it's convenient to make a change of function, so to write this function g of r here as another function f of r divided by r to some conveniently chosen power, which is turns out to be 3n minus 5 over 2. I mean, this you don't really need to do that, but it's just things are a bit nicer if you do that. And now the Schrödinger equation for the hyperradial problem looks as follows. So you have minus h bar squared over 2m f second derivative of r plus 1 over r times f prime of r plus h bar squared over 2m times, and that's the very important term, s squared over r squared plus the trapping potential f of r equal to EF. And this thing, of course, you can view it as an effective potential U effective of R. So you see that, again, it's a little bit like when you do the hydrogen atom. Now you end up with an equation for just one particle in one dimension, a fictitious particle. And here you have something which is in the hydrogen atom would be the centrifugal barrier. But here, of course, this S comes from the interactions. It depends on the interactions. So this part here, actually, it's easy to show that it corresponds to the Laplacian in 2 dimensions. So meaning that my fictitious particle actually I should imagine that it lives in 2D, and r is the distance between the fictitious particle and the origin. And f of r is the wave function of this particle, which only depends on r. It doesn't depend on the angle. So it's an S-wave particle in 2D. And this particle just solves the Schrödinger equation, so meaning that it's subject to this effective potential. So let's first look at how this potential looks like in free space. So for omega equal to 0. Then you only have this S squared over R squared potential, which is repulsive. And it will be interesting to look at what happens at 0 energy, because in this case the solution of this Schrödinger equation without the trap is very simple. It's just a power law, f of r equal r to the power s, again the same s. Now what happens in the trap? So when omega is non-zero, then of course our effective potential will look like this. It will have still this repulsive S squared over R squared behavior at short hyperradius, but on top of that there will be the harmonic trap. So it turns out that this potential actually is quite a magic potential. The first magic thing is that the spectrum of this potential is made of levels which are equally spaced. And the spacing is just 2 h bar omega, where omega is this trapping frequency. So, and actually the energies, they can be written as S plus 1. So the ground state energy turns out to be S plus 1 h bar omega. And then, of course, if you go up this ladder, you should add 2 times q, where q is an integer, non-negative integer. So that's the first really non-trivial result. So again, we are looking at this many-body problem, strongly correlated in isotropic harmonic trap. And what we just found is that the spectrum, even though it's very hard to calculate, we can say the following, that this spectrum is made of ladders. And of course, there is not just one ladder, because there is not just one eigenvalue of this problem. Actually, there is an infinity. There is a discrete infinite set of such eigenvalues. So there are many of these ladders. And it turns out that you can define quite simply an operator, L plus, which takes you from a given state to one step higher within its ladder. And this operator is the same for all the ladders. And similarly, to go down, there is an operator L minus. And so for people who like symmetries and algebras, you can show that these operators L plus, L minus, and H, they have some nice commutation relations, I mean, which are just coming from this fact that the levels are spaced by 2 h bar omega. And it turns out that these commutation relations are the ones of the SO21 Lie algebra. So that's why people like to talk about the SO21 symmetry. And it's more precisely, this is a dynamical symmetry, because the Hamiltonian here is part of the algebra, so which is different from the usual symmetry. So for example, you know, when you have rotational invariance, then you have the angular momentum, which satisfies some algebra between Lx, Ly, Lz, but they all commute with the Hamiltonian. Okay, here it's different because these L plus, L minus, they don't commute with the Hamiltonian. However, the commutation relations between L plus and the Hamiltonian, or L minus and the Hamiltonian, are simple. So that's why it's called the dynamical symmetry, or it's also called the hidden symmetry. And actually, this has some consequences also on the dynamics, as I will mention slightly later. But before that, let me continue a bit talking about this S. So first of all, it's very easy to find the asymptotic behavior of this S in the limit of a large particle number. So let me call S of n up and down the lowest S. So remember, there are many, there is a whole spectrum of values of S. And let me consider the lowest one for a given number of spin up and spin down particles. Then S of n over 2, n over 2. For simplicity, let me consider this case where you have equal numbers of up and down. In the large n limit, I can use this formula now for the ground state, so I forget about this one. And since n is large, actually S will be large, so I can also forget about this plus 1 here. So I can just say that this is equivalent to the ground state energy in the trap for these particle numbers divided by h bar omega. And now this is very easy to calculate how this behaves at large n, because as Frédéric told you, if you have many particles in a harmonic trap, you can use the so-called local density approximation, which actually becomes exact in the large n limit. And what you find is that this will be the square root of the Birch parameter. So I remind you that this psi gives you the ground state energy of the homogeneous gas times basically the ideal gas result, which turns out to look like this. So that's quite an amusing result. By using this detour from the harmonic trap, we obtained a relation between the Birch parameter, which tells you what happens for the homogeneous gas in the infinite homogeneous space. And this relates the Birch parameter with S, and S is the exponent that you have here in your wave function in free space. So because I remind you that if you look at free space, the result from what we just said is that the many-body wave function can be written as a product of r to the power s times phi of omega. And So again, this corresponds to some many-body scattering state in free space. Okay. So which is a very different, a priori, very different situation from what you have for the Birch parameter, where you have a finite density. In the infinite volume, you have a finite density. Here we have a certain number of particles, which is large, but it's finite, and we are in the infinite space. So that's why the wave function cannot be normalizable in this case. Now, if we go back to the trapped case, non-zero omega, then psi will be given by some wave function f of r, which is actually can be calculated analytically easily. It's just the eigen wave function of this potential. So it depends on S and it depends on Q, the quantum number Q, times phi of omega. And of course, this phi of omega here is the same, because it comes from the same hyperangular problem. So we arrive at another surprising conclusion, which is that this free space problem is basically equivalent to the trapped problem up to just changing this hyperradial part of the wave function. But the non-trivial part, the hyperangular part, is actually the same. Any questions? Yeah. So this fs of q, I can write it down if you like afterwards. It has a very simple form. So the main point is that actually it's not just r to the power s, of course, because it has to be normalizable. Actually, it has to decay like a Gaussian at large r because of the trap. But at short distance, you see that the potential will be dominated by this guy. So at short distance, actually, this behaves like that. So now let's turn to the three-body problem. Of course, to have the non-trivial situation, we should take some spin up and some spin down. If they all have the same spin, it's non-interacting. And then it turns out that the spectrum of S can be calculated analytically. So let me write down, first of all, the first few values. The first one is 1.77 something. The second one is 2.16 something. And it turns out that this one corresponds to a total angular momentum of the three-body problem. So the sum of the angular momenta of the three particles, which is actually L equal 1, quantum number L equal 1, while the second one is L equals 0. So it means that if you put your three fermions in a harmonic trap, isotropic, then the ground state, which corresponds to the smallest s, actually has an angular momentum L equal 1. Why not? This can happen. So so I told you that actually these S are known analytically. So let me write down how it looks like in the case L equals 0. So S is just given by the solution of the following equation, minus S times cosine S pi over 2 minus 4 over square root of 3 sinus S pi over 6 equal to 0. So if you want, the sort of Birch parameter for three particles is actually just a transcendental number which is as good as pi or e or square root of 2. It doesn't have any name in the mathematical literature, but it's the solution of this magic equation. So now, as I promised, let me talk a bit about what happens when this S squared becomes negative. And what happens is the so-called Efimov effect. So, as I said, the paradigm situation where this happens is actually when you have three bosons. So let's make a little excursion from the school and let's go to three bosons. So when you have bosons, actually you can just take them spinless without internal degrees of freedom, and the problem will already be interesting because the many-body wave function, in this case the three-body wave function, should just be symmetric now if you exchange two particles. And so therefore it should satisfy the contact conditions for any of these pairs. And then actually you can do the whole machinery that I already did. You can also do it in this case. And you arrive actually at the same equation here for these hyperangular eigenvalues S, except that this minus here is replaced by +2. It's basically because for fermions you have two interacting pairs between, these are the two interacting pairs, while for bosons you have three interacting pairs. So that's why this 1 is turned into 2. And then because here you have anti-symmetry, you have minus, here you have symmetry, you have a plus. Yes? Yes. So I mean, this is the our problem, of course, is rotationally invariant. We are in an isotropic trap. Okay. So the total angular momentum of the system is a conserved quantity. So therefore, you can separate your problem into different subspaces corresponding to different total angular momentum. Okay. So, so therefore, you have your hyperradial problem, and then you have the hyperangular problem, which is itself separated into sectors. That's all. Okay, so now actually, because of this innocent change in the equation, something dramatic happens, namely, now this equation has one imaginary solution, which turns out to be I times 1.00624 something. And for this very special value of S, of course, what happens is that now this effective potential, S squared over R squared, becomes attractive. And this is very dramatic because when you have a particle moving in an attractive 1 over R squared potential in 2 dimensions, so I remind you that our fictitious particle is actually in 2 dimensions, this problem in quantum mechanics is ill-defined. So to make it well-defined, you need to add a boundary condition at the origin. So, and this boundary condition for small hyperradius, it's actually a 3-body contact condition. Why 3-body? Because small hyperradius means that actually all our 3 particles are close to each other. So this boundary condition has to be added in the limit of small hyperradius. And this boundary condition depends on a parameter which is called the 3-body parameter. So it's a bit like the original two-body contact condition, which depended on the scattering length A, the two-body scattering length A. So this three-body contact condition depends on another parameter, which is called the three-body parameter. So actually, this boundary condition is quite simple, but I will not write it down because I don't really have so much time, and also it's not really the topic of the school, because we are supposed to discuss fermions. However, let me mention that once you add this boundary condition, then your problem is well defined, and it turns out that you have bound states, as you can easily guess, in this potential. And these bound states, they are called Efimov trimers. They are three-body bound states, of course, so they are trimers. And their spectrum is actually a geometric series, and the factor of this geometric series, so basically to go from this energy to the next one, you have to multiply the energy by e to the minus 2 pi over modulus S0, which turns out to be around 500. So that's why it's quite hard to observe Efimov physics and the corresponding scaling in the lab, but people have actually managed. But okay, that's not the topic of today. So on the conceptual level, actually this three-body contact condition has the following effect. So in the beginning we had a scale invariance, so we could rescale our problem by any scaling factor lambda, and basically the problem didn't change. But now actually this is broken down to a discrete scale invariance. So we can only rescale our problem by this factor if we are talking about energy, or if we are talking about length, it's without this 2. So this is a very rare example in nature, maybe the only one, I don't know, where we have actually a discrete scale invariance. And there have been experiments about this. We can discuss it later. So now let's go back to fermions. But for a moment, let's allow to have a different mass for the spin up and the spin down. So of course, experimentally, this means that you actually have a mixture of two different species of atoms. Now what happens? So let's begin again by looking at the three-body problem. So two spin-up particles and one spin-down particle. What happens as a function of the mass ratio? It turns out that actually, if this mass ratio exceeds a threshold, which is 13 point something, 607, then again we have an Efimov effect, even for fermions. Now, what happens when we have 3 spin-up particles and 1 spin-down? It turns out that, again, we have a threshold which is slightly lower than the previous one. It's at 13.384 something, where again we have an Efimov effect. And now this is, in this window, we have a 4-body Efimov effect. So we actually have Efimov tetramers. And this was discovered by Yvan Castin, Christophe Morat, and Ludovic Prikopenko, while this thing is basically contained already in the work of Efimov. And this is purely analytical, because the 3-body problem is solvable analytically. You have this kind of equation you can write down also for different masses, while this requires both analytical steps and some numerics in the end to solve the hyperangular problem. Then what happens when we have 2 spin-ups and 2 spin-down? Turns out there is no Efimov effect for any mass ratio. And this was found by Chipayendo and Yvon Castin. So now let's go back to the most interesting situation, or the simplest one at least, where we have equal masses. And there actually there is a conjecture. There is a conjecture that there is no Efimov effect whatever the particle number. And we can really hope that this is true, because if this is not true, then everything that we are saying, since 15 years about unitary gas and BC-BCS crossover and so on, all this is wrong. Because, of course, we are assuming that there is no additional parameter in the problem. Suppose there would be a 20-body Efimov effect, then we would need to add a 20-body contact condition and a 20-body parameter in our problem. So hopefully that's not true. And actually, mathematicians have started to understand that this problem is important. And they have, in the last 2 years, they managed to prove this rigorously. But so far only for either the 2+2 problem or for the n up plus 1 problem, so the Polaron problem, for any n up. So hopefully they can prove it also for any n down. Then we can sleep better. Okay. So next part will be about short distance scaling laws. And this is the part which actually holds for any scattering length. So again, let me consider some eigenstate, many-body eigenstate of the zero-range model for an arbitrary scattering length. And now let me ask the following question. What happens if I have my particle positions in such a way that actually somewhere I have a few particles, 3, 4, 5, or 10, or whatever, a certain number of particles which are very close to each other. So let me denote by J the set of these particles which will be close to each other. So J will be a subset of all the particles which are labeled 1 to n. And this subset should contain a certain number, let's call it Q up, of spin up particles and Q down spin down particles. Okay, so for example, if I have here two spin up particles and one spin down particle close to each other, then this is 2 and this is 1. Q up is 2 and Q down is 1. And I will also call Q equal to Q up plus Q down. So now, of course, if I consider the coordinates of these special particles, Ri for I belonging to the set J, then I can again play the same game than before. So I can define the center of mass coordinate Cj, which is the center of mass of all these particles in the set J. And I can define a hyperradius Rj, which is the hyperradius of this subset of particles, and finally the hyperangles omega j. Okay, is that clear? Now the statement is the following. our many-body wave function, psi of R1 Rn, is equivalent in the limit where all these particles are close together. So in other words, when this hyperradius Rj goes to 0, to this hyperradius Rj to the power s of q up, q down. So that's the s of this q up plus q down body problem. So in this case, where you have up, up, down, it would be the three-body problem. Minus, as usual, 3q minus 5 over 2 times phi of omega j, where this phi is actually the one that's associated with this value of s. It's the eigenvalue of the hyperangular problem for this q up plus q down body problem. And then, of course, times some a, j, which depends on cj and the other particle coordinates. And this is basically contained in some unpublished preprint of Shinatan. And it's also essentially contained for the three-body case in the paper of Petrov, Salomon, and Shliapnikov. And actually, the latter paper, what they were interested in is three-body losses. So three-body losses, they are there in experiments, and we can also have them in our simple theory models by doing the following. So remember that towards the beginning of the first lecture, I had such a plot with the depth of my square rail potential and then the binding energy of the dimers. So, and I told you that, okay, you have a first dimer that appears, but then if you go further, you will have a second one. So, and if we work, for example, around this point, then we will have here our weakly bound dimer, or if we are at unitarity, zero energy state. But at the same time, we will have here a deeply bound dimer. Or if we go to a further resonance, we will have several deeply bound dimers. And if we have this, then of course we can have three-body losses, which correspond to this chemical reaction. It's a chemical reaction where you have three atoms which turn into one deeply bound dimer and the third atom, which remains to conserve energy and momentum. And typically in experiments, as Frédéric told you, the kinetic energy of these guys will be larger than the depth of your trap, so they will be lost. And as a result, you will have a decrease of your particle number, which will be given by some rate, which is called the three-body loss rate. And what Petrov, Salomon, and Shliapnikov have shown is that this three-body loss rate, if you make it dimensionless by dividing it by the Fermi energy, it actually scales as KFB, where B is the range. So experimentally, by the way, the range is on the order of the van der Waals range for broad Feshbach resonances, to the power 2 times S of 2, 1. So this is the 1.7 something that I wrote down before. So you see that this thing actually goes to 0 in the zero range limit, when the range is much smaller than the interparticle distance. And that's, of course, extremely important, because it means that even though you have some deeply bound states, actually you have a quasi-equilibrium. Because this three-body loss rate is small compared to the other relevant timescales of the problem, which are set by the Fermi energy. So therefore, in the experiments, the fact that you have deep dimers is not really a problem, and it can be ignored for most purposes. And so how did they obtain this result? Is basically just follows from the fact that you have this scaling law, which tells you what's the probability to have three particles close to each other, which is what you need in order to do this three-body recombination to make a deep dimer, which has a small size. So this just basically comes from the modulo squared of this wave function. Okay, so in the remaining, in principle, I have 20 minutes because we started 5 minutes late, right? Maybe I will even take less than that. So I will, as promised, I will talk a bit about the dynamics. So now, let me go back to the unitary limit and back to the zero range model. And again, let me consider an isotropic harmonic trap. But now let me make the trapping frequency omega to be time dependent. So I will use a shorthand notation, capital X vector, which is the collection of all the particle coordinates R1 to Rn. So that's a vector with 3n coordinates. Then the zero range model for this time dependent problem looks as follows. So you have the time dependent Schrödinger equation, I h bar d dt of psi of x and t. So that's the many body wave function time dependent, equal to minus h bar squared over 2m Laplacian with respect to x. So that's equal to the sum of the Laplacians with respect to all of the particles, plus trapping potential 1/2 m omega squared x squared psi of xt, and that's it. And of course, you also should obey the contact condition at all times. Psi of xt should obey the contact condition at all times. And this is the contact condition with a equal infinity. So now let me specialize slightly to the following situation. At t equals 0, we have some trapping frequency, which I will call omega 0. And our many body system is in an eigenstate. So psi of x at time 0 should be an eigenstate of the problem in this trap with a certain energy E. So we are in a stationary state, maybe it's an excited state, and then we start changing the trapping frequency in an arbitrary way. So what happens? Turns out that it's pretty simple what happens. And this was found by Yvan Castin in 2004. Namely, you have a so-called scaling solution for this time-dependent problem. And it looks as follows. So our time-dependent wave function is equal to the initial wave function at time 0, just rescaled. The coordinates should be rescaled by some time-dependent factor, lambda of t. And that's the main point. And then turns out that there is also some phase factor e to the I lambda dot of t divided by lambda of t times x squared times some constant m over 2h bar. And this is quite natural because if you think about it, so what you are saying is that the gas will do some oscillations like this. So accordingly, there should be some phase factor which corresponds to the velocity associated with these oscillations. And then there is also of course, some normalization constant, because our wave function should remain normalized to unity. And of course, there is also some phase factor theta of t, which can also be calculated, but I will not write it down here. So why is this true? It's quite easy to derive. So first, you can check that this thing indeed solves if you take this ansatz and put it into this Schrödinger equation, you see that indeed it's a solution. Provided lambda of t satisfies the following equation. Lambda dot dot is equal to, and I will write it in the following form, minus d over d lambda of omega 0 squared over 2 lambda squared plus omega of t squared over 2 lambda squared. Of course, you can calculate the derivative with respect to lambda if you want. And I mean, this should be evaluated at lambda of t, of course. So our lambda of t solves this equation, which looks like the equation for the motion of a classical particle in 1D. And the other thing to check, of course, is that our scaling ansatz here solves the contact condition for a equal infinity. And this is very easy to check because this contact condition, of course, is scale invariant. The scattering length is infinite. This contact condition does not depend on any length scale. So if you rescale all of your coordinates by the same factor, you will still satisfy the contact condition. Given that, of course, at the initial time, it's satisfied because it's an eigenstate of the zero-range model. Yes. I mean, it cares, but it only lambda cares about it. Yeah. I'm not quite sure about the second question, but maybe let's discuss it later. So, in fact, okay, maybe you're asking whether anything here depends on energy. The answer is yes, actually, it's this theta, of course, which depends on the energy. Sorry, I didn't get the question, but okay, let's discuss it after. So, now let's consider two interesting special cases. So the first one is the breathing mode. So to get the breathing mode, what you should do is very simple. You should just you change your trap frequency. In the beginning, it doesn't really matter what you do, but at least after some time t1, you should just leave your trapping frequency constant. It can be back to the initial value, or it can be a different one. It doesn't matter. So you start with your gas. Let me draw this cloud of gas in the trap at some frequency omega 0. And then you change your frequency, if suddenly or not suddenly, it doesn't matter. But after a while, you should just keep it constant, equal to some value omega 1. So then what happens is that actually now this equation, where if you put here a constant omega 1, it's easy to show that the solutions of these equations are actually periodic. So lambda of t oscillates and it oscillates at a frequency which is 2 omega 1. It's easy to show if you think about what is this classical problem. I wrote some explanation in the notes. So basically what you have here is that this lambda, which tells you how to rescale the size of your gas, is just oscillating. So in other words, your gas undergoes a breathing oscillation. So basically it's just doing something like that in an isotropic way at a frequency which is 2 omega 1. And the most remarkable thing, of course, is that these oscillations are undamped. It's just periodic, without damping. So at first sight, it's of course very surprising. And of course, this is completely unrelated to superfluidity. So this happens even if you start from a high temperature, if you start above the critical temperature, it doesn't matter. So this is a consequence of the dynamical symmetry. So in fact, it's a general thing that if you have a dynamical symmetry, you will have undamped breathing mode. And it can also be understood quite easily if you think about the separability in hyperspherical coordinates, because what happens here is just that the hyperradius will oscillate. It will oscillate in its effective potential. And the hyperangles, they don't do anything, because you are in an eigenstate in the beginning, so the hyperangles don't do anything. By the way, if we start at now a finite temperature, so a statistical mixture of eigenstates, of course this conclusion remains true. So experimentally it looks straightforward, but actually it's not, because it's hard. From what people tell me, that it's hard to make an isotropic trap. Yeah. Anyway, that's an exact result, so maybe it's not even worth checking experimentally, I don't know. So, okay, but this was for weakly interacting Bose-gas. We are talking here about fermions yoke, fermions at unitarity. Hello. So now let me consider another situation. But you're right, I mean, Eric Cornell managed to do a very isotropic trap, but however, it was not an optical trap. Here we need probably an optical trap. So now let's consider a time of flight. So in other words, we just switch off the trapping frequency, and let's consider that we just switch it off suddenly. Of course, we in all this business, we keep A equal to infinity. So that's not like the time of flight to measure the momentum distribution, where you should switch off the interaction, but here you keep the interaction. And then, of course, your lambda here, now you don't have this term, so your lambda will just grow. Actually, it's easy to find how it will grow, but it doesn't really matter here. It grows, so of course your gas will expand. And the interesting point here is that if you do this, you have an exact magnifying lens. So basically your gas is just expanding, and the wave function, apart from this rescaling, doesn't change. So if you image your gas after such a time of flight, it's actually as if you would image it in situ. And by the way, there is some generalization of this to anisotropic traps and finite scattering lengths. I put the reference in the notes. It's Carlos Lobo, 2008. But in their case, of course, it's not related to any dynamical symmetry. It's just some trick that they found. So last point, I want to tell you about the consequences of all this for hydrodynamics. So that's the part, I don't know. the last part. So Frédéric told you already about hydrodynamic equations, I guess? No? Okay, he will do it. Anyway, you know, hydrodynamics is this nice theory where you have a velocity field, a density field, and since here our system is compressible, we also have we have the density field, and we have temperature field, and that's it. And all these things are related by equations. So if we are in the normal phase, for simplicity, let me restrict to the normal phase, because in the superfluid phase it's a bit more complicated, because then we would have two fluid hydrodynamics. So in the normal phase, you have these 5 quantities which are related by 5 equations. It's basically conservation equations and Euler equation. Well, it's actually not Euler, because here we have viscosity. And we have 2 types of viscosities. So the most known one is the shear viscosity, which tells you basically what's the friction, internal friction of your fluid when you have a shear. And then actually for a compressible fluid, there is another viscosity, which is called dilatational viscosity. It's also called bulk viscosity or volume viscosity. And it's denoted usually by zeta. Now, in hydrodynamics, you have also a concept of entropy, of course, because I mean it's locally you have thermodynamic equilibrium, so you have a local entropy, and if you integrate it over all space, you get a total entropy. And this total entropy, of course, should increase. So the time derivative of the total entropy is given by some nice expression, which is positive. And one of these terms is the one we will be interested in. It's the one which involves this dilatational viscosity. There is temperature, and then there is the divergence of the velocity field modulo squared, which is quite natural because, as the name suggests, so this is the viscosity which is related to some internal frictions if you dilatate your system. If your system expands, in general there will be also some kind of internal dissipation going on, and the increase of entropy will be controlled by the divergence of the velocity. Okay? And then there are some other terms which are, all of them are positive. So there is one term which is involves the conductivity, heat conductivity, and there is another term which involves the shear viscosity. Now let's consider the breathing mode. And let's ask what happens if I have many particles in my trap in the beginning at equilibrium. Then I change the trap frequency. I excite this breathing mode. Well, this breathing mode is undamped. Therefore, the entropy as a function of time will be periodic. It will oscillate without damping. But on the other hand, it also has to increase. So it's a periodic function which is supposed to increase, so therefore it has to be a constant. Therefore, this right-hand side has to be 0, and therefore zeta, this dilatational viscosity, has to be 0. So we have derived that for our unitary Fermi gas, actually there is no such internal dissipation when the gas expands or contracts. And this was discovered actually by Son, and he was not aware of the scaling solution of Ivan, and not aware of the breathing mode. And to derive this, he used something from high energy community. He is a sort of high energy condensed matter physicist at the interface. And so what he used, it's some conformal invariance in a formal curved space. By the way, high energy physicists, they say that the unitary Fermi gas is a non-relativistic conformal field theory, which, as far as I understand, is just their way of saying that it has this dynamical symmetry and this time-dependent scaling solution. Thank you. No. So this this mass ratio at 13 is pretty big, but I think that Rudi Grimm was planning to build some experiments which had this mass ratio, and when he learned that there is an Efimov effect, he decided to use another atom. Yes. Well, as I said, if you want to see this experimentally, first of all, you have to try to make an isotropic trap. Nobody has tried this yet. But of course, in experiments, you are right, it should stop at some point. And probably it will be because of some small anisotropy of your trap. Or there can be all kinds of other reasons, like the scattering length is not really infinite, or the range is not really zero. I can't think of other reasons now. Dipole mode? That's just the center of mass. It's trivial. It's the one I mean, in the beginning I said you separate the center of mass in a harmonic trap. That's always true, yeah.